I explained that we discovered a number of extrasolar planets. Now we are more interested in the extra intelligent life in another planet. Then maybe life in another extrasolar planet might not need liquid water to survive, but I would like to start considering life on the Earth. Liquid water is essential to sustain life on the Earth. Surface temperature of an extrasolar planet becomes too high to vaporize the water on the surface when a planet is located near a host star. This is star. If the planet is located very close to the stars, is too high temperatures. The planet cannot keep liquid water on the surface. High T. On the other hand, water freezes into water ice on a planet far from the stars. If the planet is very far away from the host stars, temperature is too low. And it becomes water ice. This becomes a gas. There will be a region in which a planet keeps liquid water on the surface. There is some regions. If the planet is here, liquid waters. A planet can keep the liquid water on the surface. We call this region is habitable zones. In order to find these habitable zones, we need to determine the surface temperature of a solid particles. This is stars. Stars emit light in all the directions. Isotropically, there is no special direction. Then, if you consider a sphere with the radius of the Earth, all the areas, if you take the same areas, same amount of energy is passing through each areas. Then if you take unit areas, then how much energy is passing in these regions, you can easily calculate. L is the luminosity. L is the luminosity divided area of the spheres, 4 pi r squares. Okay, this is the important quantities. Then if we place the particles on the surface of these spheres with the radius of the Earth, some of the light will be received by these solid particles. So the other part is that if we don't take into account any spin motion of the particles, this part doesn't receive any energies, but this region is going to receive the energy from host stars. Then you can consider the particles. Radius is capital R. Then these regions, areas covered these regions is pi r squares. This is the regions for a particle to receive light from host stars. Then how much energy a particle received? Received energy is obtained L over 4 pi r squares. This is energy emitted by stars and passing through the unit areas. Times you have to multiply the areas of particles. Then it becomes L over 4 times capital R over R square. This is the received energy. Then actually these particles, to determine the temperatures of particles, we also take into account the emitted energies. Energy from particles. Particles, actually we consider the spheres with the radius of capital R, is actually emitted energies following the Stefan-Boltzmann laws. Stefan-Boltzmann law said the emitted energy per unit areas. This is the Stefan-Boltzmann laws. It said emitted energy is only dependent on temperatures per unit area is only dependent on the temperatures, and this is the proportional constant of the lower case of the sigma t to the fourth. Then emitted energies from particles. The energy from particles can be calculated, sigma t to the fourth. You have to multiply the surface area of particles is 4 pi r squares. This is the surface area of particles. Okay, this is the emitted energy, and this is received energies. Always for the particles, received energy have to equal to the emitted energy. If the received energy is larger than the emitted energy, the temperature is going up. If the emitted energy is larger than the received energies, its temperature is going down. So always it's reached the balance between the two energy. This is received energy have to be equal to the emitted energy. Then received energy is written L over 4 times R over R squares equal emitted energy is sigma t to the fourth 4 pi R square. Then from this equation you can solve the T. T is the temperatures of particles. It's expressed L over 16 pi. Sigma is a Stefan-Boltzmann constant. R is a distance from host stars, and 1 over 4. If you substitute solar luminosity, the luminosity of the sun, and the distance to the Earth from the sun is 1 AUs, you can find the numbers. 280 Kelvin. This is temperature of a particle if we place a particle at 1 AUs. Then you can write that this is solar luminosities. And the dependence is 1 over 4. And for the R over 1 AU is minus 1 over 2. So if you want to find out the temperatures at R equal 5 AUs, you can just substitute 5 is here to find the temperatures. And the temperatures, actually the temperatures of the vertical lines, and R is a distance from the host stars. Temperature is actually the decreasing function, as we expected. If we have a planet is very close to the host stars, temperature is too high to keep the liquid waters. Too high temperatures. If we consider the really far positions from the host stars, temperature is too low. as we expected, there is some regions to keep a liquid waters, and we call this habitable zone. Okay, so this is the answer to these questions.